Thank you, everybody, and thank you for spending your Saturday with us, and thank you for the organizers for the opportunity to invite me to present about the adjuvants. I'm going to start apologizing for my accent. I am from Barcelona, Spain, so I roll the R's a lot, so please stay with me. So today we're going to be speaking about, I'm going to introduce you a little bit about the adjuvants, their mechanism of action, their properties, and then I'm going to be focusing in microorganism-derived adjuvants, and more specifically in the Mycobacterial adjuvant part of barricade. So what is an adjuvant? So adjuvant comes from the Latin adjuvare, that means helps, aid, or assist. And a vaccine adjuvant is a component that potentiates the immune response to an antigen and modulates it towards a desired immune response. And it was quite funny because the term adjuvancy was realized when there were in different lots of vaccines. They found that there were different grades of efficiency. And then they found that the lots that they were produced with dirty glassware were the ones that they were presenting more efficiency, more immunoreactive. And they found that was due to contaminants present in the glassware. And so now you have vaccines like the diphtheria, tetanus, and pertussis, the DTP, that you have the diphtheria toxoid, the tetanus toxoid as cellular components of the pertussis, but also you have glutaraldehyde, formaldehyde, phenol, aluminum phosphate on them because helps to potentiate their adjuvancy. So this is the antibody titer that you will obtain when you give an antigen. And you will see that over time, the antibody titer goes up and then decreases over time around 100 post-days. However, if you do it in the presence of an adjuvant, you will see that first you can produce a bigger titer of antibodies, and it maintains over time. So types of immune responses, I'm going to use to browse a little bit because Dr. Aranya already mentioned them a little bit, but we're focusing in the net immune response. The adjuvants will trigger this very well. Okay, it's going to bring to the site of infection antigen-presenting cells, innate immune cells, that can be macrophages, dendritic cells, neutrophils, that is going to help to be loaded with antigen that we want, so then they can go to the lymph nodes and present it to antigen T cells. Then, of course, we have what we are trying to do with a vaccine, that is to potentiate the memory. So we have the adaptive immune response and a specialized immune response that, after we get vaccine, we keep it as a memory defense. So when we get reinfected, we answer and we eliminate the microbe very fast. What are the functions of adaptive immunity? Well, it's mainly to recognize non-self from self during the process of antigen presentation. And the reason is because you want to avoid autoimmunity that is going to be not prejudicial for us. So what an adjuvant does is to be a composition of what we call it microbial associated molecular patterns. These are molecules from microbes that have been evolved with us for many years. So the adjuvants, when they have this composition, will trigger the antigen presentation process in a way that will benefit us. There are also generations of control to maximize eliminated specific pathogens or cells that have been infected with pathogens. And this is the most important thing, okay? We have created a memory response, okay? And also that can be done by antibodies or a cell-mediated response. So we have 3 types of the memory responses. We have the memory T cells, the memory B cells, and the humoral response that we're targeting during a vaccination process. So the memory T cells. So when we induce a vaccine to the site of the vaccination, we have a dendritic cell, antigen-presenting cell that will capture the antigen and is going to go to the lymph nodes. In the lymph nodes, it's going to be recognized, it's going to present antigen by a specific receptor to a T cell that also have a specific T cell receptor that will recognize antigen. Also, it's very critical to have these cumulatory molecules that will tell this T cell that this dendritic cell is activated. Over time, this cell is going to create a storm of cytokines and chemokines that as a response to recognizing this antigen, and it's going to proliferate. It's going to activate and proliferate, creating a lot of T cells, coral effector T cells. These effector T cells are going to run to the site of infection, and it's going to control the infection. Over time, these T cells will start to die. Then some of them will remain, and they call it memory T cells. These memory T cells, when is are exposed to a pathogen, they're going to be, especially if they are presented in the tissues as resident memory T cells, they're going to interact directly with an antigen presenting cell that is going to present the same antigen related to the same pathogen that they saw before. They don't need, in this case, the costimulatory connection, so they're going to respond very fast. They're going to proliferate, and they're going to control the infection very well. And over time, it's going to repeat the cycle. Okay, they're going to start to die, they're going to have secondary memory T cells, and they're going to carry on in our body. So this is what we want to target during our vaccination process. Just to show you the type of memory T cells that we have in our tissues and also in circulation, we have different types of T cells. We have central memory T cells, we have effector T cells, we have stem cell T cells, and we have resident T cells. There are some tissues in which they only have resident T cells because we don't want to have, for example, in our guts or in our intestine, effector T cells that are very reactive because these kind of tissues are exposed to pathogens constantly. And finally, we have also the memory B cells. They also, like in the case of the memory T cells, they die over time. They only are going to produce antibody again when they are exposed to antigen. And here we have an example in which we have a vaccine A, that is provided. And you here in the y-axis, we have the antibody titer being produced by this vaccine. And you have that it will take around 21 days to produce a very nice titer of antibody. However, if we do a burst vaccination in combination with another new one, around 60 days, you will see that immediately is produced and is even stronger, but will cause the protection. However, you can see also that is very specific to the first antigen that the vaccine presented, because a second vaccine also will take this as around 21 days to see it again. And finally, we have the humoral response also we want to target. Okay, we have the B cell that is going to be recognized by the microbe, and in contact with the helper T cell is going to differentiate to a plasma cell, and is going to create these antibodies. And these antibodies have different functions. We have neutralization; they can bind to the microbe and avoid infection. We have that also they can opsonize the microbe and allow that is a presenting cell to uptake the microbe and be killed. Or also that the antibodies do is activate the complement system, in which will allow directly this complex system to perforate and kill the microbe during the uptake process. So keeping this in mind, the purpose of an ideal adjuvant is first to be safe. Safe for the animal that is going to be vaccinated, but also safe for in the process of making it. You don't want to take, for example, an hypervirulent strain of Mycobacterium tuberculosis that may be an ideal adjuvant, but at the end of the day, growing it and etc. is going to be very expensive. It's not going to be safe for the people that is doing producing it. It's not going to be easy to handle. Okay? You also want the adjuvant to be biodegradable and immunologically inert. Okay? Needs to be stable with regards to adjuvancy and cytotoxicity. This means that when you have an adjuvant, when it's degraded and etc., you don't want to be a preform that then when it's degraded becomes cytotoxic to the cell and kills the cell. You want to avoid apoptosis, you want to avoid necrosis, you want to avoid cytotoxicity as much as you can when you choose an adjuvant. And also, of course, promotes an appropriate immune response to the site of delivery of the vaccine. Why to use an adjuvant? Well, as mentioned before, to facilitate immunogenicity of purified and synthetic antigens, which are poorly immunogenic. Okay, this will allow us to use less of these antigens that sometimes cost more than the adjuvant per se. It will help for antigen presentation and uptake of the antigen. The The adjuvant will require to eliminate boosting. Also, that's extremely important. And, it's going to also to help us to select the immunoresponse that we want, a Th1, a Th2, a Th17 response, driven by interferon gamma, by IL-4 or IL-17 response. And it's very important also because an adjuvant will help to boost the immune responses, especially in neonates, that they have a very mature immune system. So an adjuvant mechanism of action, as I mentioned before, is to protect the antigen, okay, and this will allow us to deliver the antigen slowly. And the delivery of an antigen very slowly helps because will allow the organism to prime T cells slowly, and more priming more slowly, more they will come to the site of infection. There are also adjuvants that may interact with specific receptors that trigger a pro-inflammatory response very fast, like Toll-like receptors, and assisting the increasing capacity to cause danger signals, so chemokines and chemokines to the site of infection that will bring the storm of the adaptive immune response to the site of infection. And assist to the translocation of antigen to the lymph node when it's going to be present to the T cells, to be primed. And remember that it will create the memory T cells as we discussed previously. So the type of adjuvants, there are many types of adjuvants. You know that there are oil-based adjuvants, aluminum-based adjuvants, LPS is using as an adjuvant, etc. But we are focusing more here in the microorganisms adjuvants because they are formed by specific associated molecular patterns that will allow us to create an extremely important innate and adaptive immune response. And we're focusing the Mycobacterium species and also the correlated Corynebacterium parvum species to Mycobacteria. The majority of the cell wall components of these microbes here are based in the peptidoglycan, and especially in the monoamyl dipeptide. This is a great adjuvant. Also, is a great adjuvant LPS. Also, is quite cytotoxic sometimes. So, there is a way to detoxify LPS to make it to use the monophosphoryl lipid A as an adjuvant. And in the case of Mycobacteria, we have the triallosimycolate. This is a very good adjuvant, but it creates a very big and very fast pro-inflammatory response. So I'm going to show you a means where we can reduce this if we can balance it. And all of them, majority of them, goes through Toll-like receptors. So now we're going to go to my field. Okay, I'm working with Mycobacterium tuberculosis pathogenesis. So I'm going to tell you the reasons why we choose a Mycobacterium species adjuvant. These are a lot. I don't know if you can read it from the end, but these are all the Mycobacterium species that have been described. And we mainly characterize them to be a slow grower and pathogenic, like Mycobacterium complex will be here, formed from Mycobacterium africanum, Mycobacterium tuberculosis, Mycobacterium bovis, related in here. There are slow growers, non-pathogenic. Okay, we have some of them here. Of interest when you make an adjuvant is that they grow fast, right? M. tuberculosis has a replication time of 24 hours. So you want something that replicates faster. If not, to see a lot of production will be problematic. So we have rapid grower, but they are pathogenic. Remember the safe problems that this confer. So we focus more in this group here, rapid growers and non-pathogenic. And why we do that? Because this is the cell wall of Mycobacterium tuberculosis, and the Mycobacterium avium and Mycobacterium alveoli, Mycobacterium vaccae all look exactly the same. Okay, they are similar, not identical, but they are similar. We have the plasma membrane. On the top of the plasma membrane, we have a complex structure composed of an arabinogalactan, and in the top of this arabinogalactan, there are these perpendicular lipids called mycolic acids. There are up to 80 carbons, but they are very long fatty acids. And and on the top, there is this peripheral lipid layers. Okay, that is the best thing that we have for the adjuvancy, because in this case, we have a mycobacterial cell lysate. Okay, so all this structure here is going to be pelleted, and what is soluble is all these components here, okay, that are unique for Mycobacterium tuberculosis. So from the perspective, we have here the arabinogalactan with the mycolic acids, and on the top we have all these, what we call it, virulent factors that the Mycobacteria utilizes to recognize the host cell. Okay, the host cell interacts with all these components here. And some of them are, as I mentioned before, the Torrelles mycolate that is currently being used as an adjuvant. But we have other components, and actually the balance of all these components is what makes an adjuvant very good. Because you don't want to have too much of Torrelles mycolate, because, especially when you use a nasal vaccine, a delivery of an adjuvant is going to collapse the lungs of the animal and will kill it very fast. Because the immune response that is going to generate is going to be very strong. So some examples of the lipids that there are present in the cell wall of Mycobacteria. We have the Torrelles mycolate, we have sulfolipid 1, the acyl trehalose, and phosphatidylinosytol with 2 dimanocytes. All these reduce pro-inflammation. But it's good also to have some that they don't induce pro-inflammation. They use anti-inflammation, so you have a balance. Okay, like in the case of phosphatidylinosytol, hexaminocyte. So when we analyze which will be the perfect Mycobacterium species as an adjuvant, the thing that we do is take different Mycobacterium species and we extract their lipids with organic solvents, with chlorofluoromethanol 2:1, then with chlorofluoromethanol 1:2, and chlorofluoromethanol water 10:3 ratios, and we combine them together. And then we use thin layer chromatography, and we spot around 100 micrograms of lipid, and we develop it. And depending on their polarity, these lipids are going to migrate. And then we are able to visualize, okay, where there are the Torrelles mycolates, and you can see here different strains of Mycobacteria with the Torrelles mycolate present here, where there are the phosphatidylinosytol monocytes that are also pro-inflammatory or the ones that are anti-inflammatory, and you can see the ratios. And you don't want to have one that only have pro-inflammatory molecules. You want to have one that has a balance between them, and this is how we choose our adjuvants. This is an example of different components of the Mycobacterium species that they are pro-inflammatory, anti-inflammatory, and where in which species they are present. Okay, you don't need to read that, but you can see that there is a lot of diversity in this field. So it was not an easy task to try to figure out which was the perfect one. Another thing that is very important is the lipoglycans and glycolipids present in the cell wall of Mycobacteria. The reason is because you see this large lipoglycan here that I think that you show that have been used as an adjuvant actually triggers an anti-inflammatory response. And it's critical that we have this in our adjuvant because it's what is going to produce us this balance. Lipomannan is another lipoglycan present in the Mycobacterial cell wall that triggers pro-inflammation. This one here also, the phosphatidylinosytol dimanocyte also triggers pro-inflammation, and this one triggers an anti-inflammatory response that is the hexaminocyte 1. How we purify them? Well, we grow hundreds of liters, and we lyse the cells, and then we run an SDS page, and we look for these components, liporabinomannan, lipomannan, and PIMS, by doing a periodic acid silver staining, and you can visualize them there. And we're able also to purify them by column chromatography, placing column exclusion chromatography, and you can see here the liporabinomannan, the lipomannan, and the PIMS. This is just to show you all these different components I'm speaking that are present in the adjuvant when they trigger a specific receptor present in the host cell, what is the outcome. So here we have, lipomannan, lipoproteins, the lower order phosphatidylinosytol monocytes, some glycolipids like Torrelles mycolate, they trigger through the toll-like receptors and induce pro-inflammatory response. Again, then you have the balance. You have the monoscapular liporabinomannan that was mentioned before, or the hexaminocyte phosphatidylinosytol that goes through the mannose receptor and trigger an anti-inflammatory response. They also reduce antigen presentation. And the reason is because they are able to block the phagocytic fusion. Okay, the same happened with DC sign. They trigger an anti-inflammatory response. This is the major receptor present in dendritic cells. They also can be opsonized, and they can go through complement receptors and have a limited pro-inflammatory response, or they can, react with some components of the lung mucosa, especially during the intranasal delivery, and they can trigger also different responses. So everything is a balance. You want to have this balance in a way that, is going to be effective, okay, but it's not going to influence in a way that will not be good for the host that will receive the vaccine. Again, you have here major cell wall components present, specifically, is what I was mentioning before. There are hypervirulent strains of Mycobacteria that are very rich in phenolic glycolipid and triglycerides. This will kill an animal in 6 hours after being delivered. They will collapse their lungs very fast. The immune response at this area is brutal. So you want to avoid to have too much of this in your adjuvant. So you want to have like a balance between them. You can see through which receptors they go, okay, if they affect or no antigen presentation. For example, in the case of LAM, yes, it will affect antigen presentation, but it's a balance that you need to be there, but there are many that will not. Okay? If they cause pre-inflammation, anti-inflammation, and they are seroreactive, and it produce cytotoxicity or no. So you also want to balance the cytotoxicity levels that these adjuvants will produce into your cells. Finally, I want to focus in the importance of this molecule, okay, associated to the mannose receptor and DC sign, okay. They also can signal. So it has this non-reducing end here will bind to the mannose receptor and DC sign and trigger an anti-inflammatory response. But their GPI anchor, where the lipids are, can signal to TLR1 and TLR2, and depending on the number of fatty acids that they have, also can signal to TLR4 and cause pro-inflammation. Okay, so also in this case, it's very important to avoid to make micelles. Okay, if they have micelles, the lipids are going to be covered, they're not going to be shown, and it's only going to induce pro-inflammation, an anti-inflammatory response. If you have a perfect balance, you may take this compound that can produce a pro-inflammatory response. So the balance of how much adjuvant and how much of this molecule is in the adjuvant is very important. Regulate antigen-presenting cells. Antigen presentation also is involved in antigen processing and can stimulate CD1 restricted T cells. And of course, this is one of the important things, inhibits apoptosis. Okay, they allow us that other components can do their job when this component is avoiding the apoptosis or necrosis of the cell. And finally, it was uncovered that all this was through the PPR gamma molecular switch present in macrophages. And at the end, the adjuvant wants to do all this. Okay, we have the Mycobacterial lysates, is going to interact with the antigen-presenting cell, and is going to generate TNF, IL-1 beta, that will trigger the inflammasome and interferon gamma, so it's going to activate antigen-presenting cell. The antigen-presenting cell is going to be working to enhance antigen presentation, exposing MAC class 2 or class 1 on the cell surface, and it's going to be able to move then, if it's a dendritic cell, to the lymph nodes 2 to antigen presentation and activate antigen presenting specific T cell response. They also are going to trigger chemotaxis. It's very important because, production of chemoattractants are going to bring to the site of the vaccination other residential phagocytes that are present there, so they're going to be exposed to the antigen, and also it's an acute phase response. Okay, it's not a chronic response, it's and then goes away. So in summary, the adjuvants are essential to develop new and improved vaccines. They can develop a successful vaccine adjuvants by a balance. Okay, this is what my message is today. It needs to find a balance here. So it can cause a nice pro-inflammatory response that they're going to bring more antigen-presenting cells to the site of vaccination. These antigen-presenting cells are going to go to the lymph nodes, are going to prime T cells, and are going to develop a very beautiful memory T cells. You don't want one that is going to cause, destruction here in the site of vaccination. You don't want an adjuvant that is going to cause necrosis of the cell, because then it's not an efficient adjuvant. We need to keep in mind that to develop a new adjuvant, safety and cost, of course, but understanding the mechanism of adjuvants is very important. You need to understand, what is the best balance present there, and develop an appropriate delivery system for them.